Okay, so welcome to today's webinar about recycling and all about construction materials and mining waste. This webinar is part one of the webinar series regarding recycling. So 3 more will follow throughout the year. It's really a pleasure to welcome you here. My name is Dr. Tanja Butt. I'm working as a product manager at Retsch, and hopefully we have put together some nice slides and some nice idea in the demo part of this webinar. And yeah, so if you have any questions, just type them in the chat function. So it arrives in a private chat room. We will answer it, and then you receive the answer, of course. If we miss something, we go through it afterwards and you will receive your answer anyway. If there's some question of more in general interest, I will refer to it at the end of the webinar, I think. And you will receive an email in the after the webinar. There will be a link for download package, which also contains the PDF of the presentation. So don't be afraid if you if you miss something, or if I am too fast in explanations, then you can go through it in each detail, and also the recording will be available. And yeah, the importance of the recycling, I think, is clear. We have the aim to reduce waste and the consumption of water, solvents, and the raw materials to save energy, environment, soil quality, and landscapes, of course. We need to minimize emissions, carbon dioxide, or pollution, and landfill requirements. And of course, we like to create something new, new APIs, for example, or new absorber materials. And maybe we can also use biogas to gain heat. So aims of recycling are very versatile and very urgent, I think, and it's a very interesting topic. So where we can use the Retsch, or where we come into play, is when we need to analyze waste material. So we need to homogenize it for quality analytics, quality control. This might be sieving. This can also be, for example, a determination of heavy metals. And as soon as we know that the material is okay for reusing, we need to crush larger sample materials. And also here we have some solutions maybe for homogenization of the sample materials in larger scale. And here we can see what are the topics of today: the homogenization, standard deviation, the correct analytical values. And then I'd like to show you how to find the optimal method, the optimal mill for a sample, for a specific sample. Suitable laboratory mills for homogenization, also for larger sample quantities. I will show them, of course, and then we will switch over to the demonstration of some of those mills in our lab. And after that, we will have many application examples for best practices before we go to talk a little bit about sieve analytics. Not in each detail. There are other webinars which you can listen to where we have this in focus, but maybe a short glance to this. And of course, also how to press a stable pallet for XRF analytics. And one slide, how Retsch Mills can be also useful in scientific purposes. And of course, if there's still time, some questions in the end. So milling tasks. Analytical methods, they are various ones for, let's say, solid materials. It can be HPLC or GC or XRF. And for all these different analytical methods, you need to prepare your solid matter to grind it and to homogenize it in order to get reliable and representative sample and reliable and representative analytical means in the end. And if you do not do this or correctly, then you can put in as much money and time in your analytical device, but the results will not be that good. You cannot compensate any errors you make in the sample preparation with a very nice analytical device. So here we know that we are in the beginning of all this quality control steps, but it's required and necessary. And hopefully I have some slides to show you also why. For example, we have this Lego bricks, toy bricks, and now the goal is to get only a few or a little amount of that for the analytical task. And if we do not grind it, then maybe we select to take a red one, but the red one might be of another composition than a green one, and so the result will not really be reliable, not representative for the complete sample, and also not reproducible. So we need to homogenize it to mill it. And when we have this coarser fraction, if we take some milligram, then maybe this is okay. So we can try to analyze it, but maybe we have more green particles than yellow ones or more blue ones in it. So really not that homogenized than it could be. And as soon as we have a pulverized, then it is completely independent where we take our few milligram. The composition is always the same and contains the same amount of red, green, and blue and yellow bricks, and it is reliable. It is really representing my original sample. So grinding and homogenization is really crucial to get reliable results in the end. And this can also be seen in this example when we analyze sulfur content in rubber and we ground it in one experiment to 3 millimeter blue, or in 300 microns red line. And we took different part samples and analyzed them. You see that the green, blue ones very much more in the sulfur content. So this is not enough homogenization, obviously, because we get a higher standard deviation and more varying results. It's not reproducible. So proper grinding here shows good results in the end. And we get often the task, okay, how fine shall I need to grind my sample? And this is not the right questions, not as fine as possible, only as fine as needed. This is the really right question, because when we only need about 0.5 millimeter size to get reliable results in the end, then there is no why grinding much more. Then it's only wasting your time, your money, and maybe also your machine, the abrasion. So only as fine as needed and not as fine as possible. Yeah, the finer you like to get the particles, you exponentially more time to create those. And the fineness is also easy. We need to define fineness to talk about it before and after. For example, here, this rice sample, we have a D50 of 3 millimeter particles. This means that before grinding, the sample is 50% of the sample is finer than the 3 millimeters. And after grinding, of course, it gets smaller. And now we have half of the particles finer than 40 millimeters. And also the particle size distribution curve is different, more narrow after the grinding. Yeah, so we have changed this as well. And now we have a comparable value, which we can try to reach the next time again to be reproducible. And we need to talk about abrasion. Abrasion is an important factor because we cannot avoid it. Means when we use steel tools for or in our mills and crushes, we will find some steel and ppm in our sample afterwards, which can also be seen here when we grind glass, which doesn't contain any steel, but we use steel tools in red. Here you see that the powder also gets a little bit grayish, so we can obviously see that something happened with the material. And when we use zirconium oxide tools shown in blue, then it stays a brilliant white powder. And we also see that we do not get any signals for iron in the zirconium oxide sample, so the glass ground in zirconium oxide tool sample. But we see some signals for steel in the glass sample, which was ground with steel, of course. And this is abrasion. We cannot avoid it. We can only choose the material of the grinding tools that they do not disturb the following measurement. Yeah. And this is also true for example, temperature increase or for heating the sample up front. Then we can maybe grind it easier, but if we like to analyze for moisture content, then heating is not good because it falsifies our results. And also we need to make sure that there's no cross-contamination. So easy cleaning is crucial as well, so that you do not find parts of the last sample in your new sample, and then you get false results in the end. Then I'd like to also show you how we can grind particles. We use 5 grinding principles. For hard sample materials, we use pressure. That's easy, I think. You just go through it and apply pressure to hard and brittle materials. You can also use impact. So you take a glass bottle, throw it against a wall, and then you have the impact event and it's pulverized, smashed. Then we can use friction for stones, but also for softer materials to come to finer particles. We can use shearing effects, like cheese, so where particles are just sheared. This is not for hard samples, not for stone, but for maybe wood or softer materials. And of course we have cutting, cutting as well. Again, not for stones, but for softer materials. It's quite nice. And in our different mills and crushers, there are these grinding principles used, single or in combination, to effectively crush or grind the samples. Okay, I need to go to the next slide. Technique. Okay, let's talk about our portfolio. We have more than 35 mills divided in different groups like jaw crushers or knife mills or ball mills. And I think for the construction mining materials, we talk about jaw crushers today, but also cutting mills, rotor mills, vibratory disc mills, and ball mills mostly. And I cannot go through it in each detail. There are our web pages and you can inform yourself easily with different videos and so on, but I can show you how we can pre-crush hard and brittle sample materials. Yeah, there are the jaw crushers, the hammer mill and cross beater mill, which we can take, and let's show you how the jaw crushers work. You see that the material is just coming to the grinding chamber, and then the jaws are moved, and via pressure you can crush each hard stone, and then it is fine and is collected in a receptacle, for example. Just again, I'm struggling with the technique with this. No, sorry for this, but the videos are really sometimes a bit difficult. Okay, this seems not to be a video. I'm sorry for this, but this is also easy, and I promise you there will be in the download package a video how which shows how a hammer mill works. So imagine you have here the rotor. Yeah, in this rotor there are some hammers, and when you rotate it, then the hammer also rotates, and each particle which is going through the rotor is smashed by impact, and then you have here a bottom sieve, and as soon as it's fine enough, it is collected as well. And then we have the cross beater mill. Again, I think there's no video. No, cross beater mill also works with this rotor and with impact, and as soon as a particle is fine enough, it falls through the sieve and is collected. Then we have fine grinding of hard and brittle materials. Planetary ball mills, for example. Here, I'm sure, yes, this is a video. And to show how this works, you have the grinding jars, and you put in grinding balls, and then you put in your sample, close it, and put it in the machine, and you move it on the circular way. And now there's a really huge acceleration of the balls inside, and they crush the sample inside by impact and also by friction. Yeah, and this is really a nice way to come to pulverized samples quite quickly. Here again, this is not a video, but in a nice picture, we have the vibratory disc mills, which are also shown later on in the demo part. So you can see easily how they work later on. But here you have the grinding bowl, and here you put in also disc and grinding ring, and also with movement of the grinding ball in a circular line, you can pulverize the I'm sorry. Okay, so next slide now. Yeah, then we have pre-crushing of soft, elastic, and fiber samples. Here we maybe need not a jar crusher, but for example, cutting mills are quite nice. Let's talk about then the cutting mills, and here we have also a video. So I will shut off the tone. Yeah, cutting mills, for example, to pulverize used wood or some softer materials like glass wool, for example. Here we use a rotor, but it is not the impact. It is cutting and of course some shearing effects. When the sample material is just belonging or going into the mill easily, you see this, then it is cut with a rotor. It is not suitable for stones. You can easily imagine when I throw in a stone, you will only destroy the sharp blunt knives and the stone will be intact. This does not work. Yeah, so it is for pre-crushing of softer materials. Okay, then we have fine grinding of soft, elastic, and fibrous materials. There's the ultracentrifugal mill, for example, again, a video. So imagine now the wood is pre-crushed. You have wood chips, maybe 10 millimeter size, and now you can put them into the ultracentrifugal mill ZM300. This video is with mace, but it can easily be some wood particles. And now we have a rotor, which is very, very fast rotating, up to 23,000 RPM. And you can imagine everything which is, coming to this rotor is accelerated very, very quickly or very fast and smashed on the teeth of the rotor. And as soon as it's fine enough to pass the sieve, it is collected. So this also does not work with stones, but for sample materials like wooden parts, it is very nice. And of course, we have the mixer mill, again a ball mill here where the ball is trapped in a jar again, and now it is moved from left hand to right hand side in horizontal movement, not in circular movement, as I showed previously with the planetary ball mills. And everything now here is mainly crushed by impact glass particles, stones, and so on. So really a useful instrument. And the choice of the mill depends on the milling task. So you need to consider the feed size, the final fineness, and the sample amount. And then you come to a good pre-selection of the machine. And of course, you need to have a closer look on the time and the handling. So what is my feeding time? What is the sample throughput, the grinding time, and of course, how much time do I need to clean the device? So we try to make them as best cleanable as possible, but we cannot really avoid cleaning tasks completely. So and we have some boundaries, subsequent analytics, industry, some specifications, which maybe tell you which machines you have to use. And the right accessories are also very crucial. So for example, for sample feeding, as I have shown you in the video of the ZM, or we can also use a different collecting system for having a cyclone separation unit and another collection vessel, which allows maybe for 5 liter collection, instead of only 300 milliliter when I don't use it. And of course, we have the different grinding tools, which allow me to adapt it to my specific sample. And when we're talking about abrasion again, as I showed you before, we have to talk about the different tools and the different materials we have for the tools. Here for grinding tools and ball mills, we have different materials for the jars and the balls, for the rotor mills, for the rotors mainly, and in breaking or in jar crushers for the breaking jars. And this has really an impact on, of course, the abrasion I get. As I told you before, when I try to avoid or when I need to measure heavy metals or iron content, then I should maybe not work or with steel materials. I can then choose wolfram carbide, tungsten carbide, sorry, or some hardened or zirconium oxide, for example, to avoid this metal abrasion. And we need to talk about the density, because when I need to grind in a ball mill, for example, a very tough material or very hard material, then I need to get a certain energy input, and I cannot get this with a material like agate, which has a low density. Yeah, it cannot be accelerated that much, and it will not smash the hard particles. You need stainless steel, or tungsten carbide. And the hardness is also important. When the sample is harder than a material I used to grind it, then I have a problem. Yeah, so always choose a grinding material which is harder than the sample. Okay, and then I told you that we have, yeah, of course, some mills which have the option to grind larger sample sizes or work with higher sample throughput and large sample amounts. So BB500, BB600, for example, are a good choice when I need to go for a larger initial feed size. Also, the TM300 allows for doubled initial feed size compared to PM400. And sample throughput is also interesting, of course, in the larger jaw crushers, or in the RS300 compared to the maybe more commonly used RS200, because it has larger vessels. You will see this in a few minutes. And sample amount as well, yeah, TM300, RS300, BB600, these are the choices where we can really grind or cope with larger and bigger volumes. But some words about sample preparation. Sample division is very important as well to be considered. Later on, I have also a slide for the PT 300, but now some theoretical, not only theoretical, but some data. And here we have, for example, the task that we only can have a part sample analyzed of a heap of sand in this case. And if we only take randomly a part sample, then maybe one takes one of the top, one of the bottom, and then one has larger particles and the next one has smaller particles. And who tells me that the composition of these particles is the same? So maybe we have a sample segregation here by just taking a part sample. And this, of course, is a problem because it will affect my analytics. And this means we need to talk about sample division as well. And when we just give you some values which we see over different materials for different methods and so on, then here's a rough estimation or a rough median, let's say, what we saw over the past years, that with random sampling, you get a standard deviation of about 10%. You haven't ground anything, you haven't analyzed anything, just by the wrong sample division, you get this deviation. You can cone on quartering, then it gets a bit better. Sample splitting, then it gets also better. And by automatic sampling or sample dividing using our PT100, PT200, or PT300, for example, then you can get the standard deviation to less than 1%. So really reliable and really reproducible. Yeah. Okay, now I think this was a quick overview about grinding principles, the mill, sample preparation, and process parameters, which gives you a good feeling about having the choice for your sample. And I think now it's time to go into lab for a little live demo before we go back to the slides with many application reports and also some words about sieving. Yeah, see you in the lab.
Okay, so welcome on our demo lab. I think after some slides it's time to have our live demo session, and this will be done by my colleague Dr. Gerhard Beckers, who is in the application support team. And I think I can just hand over to you to explain our systems to crush the hard and brittle sample materials.
Yep. Thank you, Tanja. Hello, my name is Gerhard Beckers. I'm working here at Retsch for about 17 years now. So I think I've got some experience anyway.
You have.
Just to show some units that we use for crushing or preparing samples from recycled material. I would like to start with the jaw crusher BB300, which is a very robust unit, normally used for pre-crushing of samples. A jaw crusher is used to grind the sample by pressure, so you've got two jaws like a V. and one jaw is moving like this, and when the sample is dropping down, it's set under pressure and it's pressed and crushes into pieces, dropping down into the receptacle here. With a screw that you can see here, we can adjust the not moving the fixed jaw backwards and forwards, so we can adjust the size of the gap so we get small or big particles at the end. Here, for example, I've set the jaw crusher to a gap of about 5 millimeters. So we've got a receptacle here where the sample is collected in. Just slide it in. And then closed. And I would like to crush a simple brick like this, down to a few millimeters. Well, it's now placed in.
Okay.
It takes some seconds, but as you've seen, the whole brick is crushed quite easily.
Yeah.
When I open the door, well, it's a bit dusty, of course.
Yeah, okay. Yeah. We have some words about this later on. Oh, cool.
So then we've got the sample here.
Yeah. Okay, maybe you can go to the detail camera.
I will show you what we've done here. Tanya, would you please?
Yeah.
So this is now the sample after crushing. You can see here we have got some powder, but we also have got some big particles. Like here it's a bigger one. See, although we've got this gap of about 5 milliliters, we create also pieces of about 10. So this depends on the breaking properties of your material, but just to show what is the result after crushing. Now I will now take the whole sample here over to another unit. And as you've seen, this is just the pre-crushing of the material. But what you normally do, you want to have a finer particle size. So for XRF, whatever, you need a particle size of below 100 micrometer. And for that unit, for that reason, you can use a machine like the vibratory disc mill.
I have just a question. So when we use the jaw crusher for the pre-crushing, do we get a defined final fineness, or is it more or less different?
Yes and no. As you've seen, with a gap of about 5 millimeters, we still have big particles in here. Longer sliced particles, but again, it's just a pre-crushing unit, not used for a defined particle size at the end. So it's the first step, and then the next step is for the defined particle size that you need for your analysis. Yeah,
great.
So I would like to use a vibratory disc mill now, which is shown here, and this is a big unit where you can place in grinding sets of up to 2 liters, and now we can crush in here about 1 liter. I will just take some sample. So it's filled in, just to show it better. It's now around about 1 liter of sample, which I've placed in. Then the lid is placed on, and inside this grinding set there is a disc which is free, can move freely, and then it's just sliding inside. I will now show how this machine is working. Putting in the grinding set into the mill. Okay. Very good to have this unit because it's a very heavy piece.
Yeah, that's great. So for the demonstration reasons, I think we will not grind too long here because it makes no sense to go for up to 5 minutes. So we will just do it for 1 minute to see how it works and which fineness can be achieved then. But for really fine grinding down to less than 100 microns, you maybe need more than the 1 minute we will do here in the live demonstration.
Normally 3 to 5 minutes with this unit. I will just explain how this is working. So we've got the holder here for the grinding set, which is, as you can see, can move freely, and underneath this motor, which is rotating this piece, so it's just wobbling around, and then the disc inside this big grinding set is just sliding inside, creating a lot of friction and grinding everything which is in its way.
Yeah, okay.
So here's a pressurized air which presses this piece down to the grinding set, and then it's fixed properly inside the holder.
Yep.
This is done when the unit is closed. You will hear this now when I lock the unit.
Yeah.
Now there's the air coming in, and now it's fixed properly. And then I can start the whole unit. This will now take a minute, so don't worry.
Yeah.
You will see when it's finished. Okay. starting rotation. I will explain later on.
Staubwisch.
Should be a bit noisier.
Oh, that's fine. Maybe it's already fine enough.
So about 30 seconds to go.
Okay.
So the grinding is stopped. The jar is released. And then we can unlock the door.
Yes.
We'll pick out the grinding set.
What happens if we have maybe not that much sample material? So this is the largest grinding set we are using right now. So what about the smaller ones?
You also can use grinding sets of 1 liter, 800 milliliters. This is standard for this machine. But we also have got, it's also possible to use the grinding sets from the vibratory disc mill RS200. So down to 250, 100 milliliter, with some adapters that can be used here as well.
Yeah, so if you have an RS200 and quite good range of accessories, you can just bring it in here and use it.
So just to show what happened in here, I'll pick some sample.
Yeah, that's good.
So this is a pre-ground material. I will just turn it around so you've got a better view. Yeah, it didn't work that properly because it's quite full, this machine.
And it was just 1 minute.
Yeah.
It was just 1 minute.
Normally below 1 millimeter, but with a prolonged grinding time, you will get a much finer result at the end.
Yes. Yes.
So this is the idea of how to grind with a jaw crusher and afterwards the batch grinding in a vibratory disc mill.
Yeah, okay. We have seen here when we opened the jaw crusher that there was a lot of dust. So how can we prevent this?
First, it's possible to connect a vacuum cleaner here, so you can remove the dust with a vacuum cleaner, which is good help. But as you've seen, you've got a continuous grinding of the stones with a jaw crusher. Then you have to pick out the sample, move it to the into the grinding set, and have afterwards fine grinding in the second step. This is additional work, and you just can grind a batch.
Here.
It is also possible to do this directly continuously, so a jaw crusher and a direct fine grinding in one step. And this is done with the unit we see on that side here.
Yeah, great.
It's now completely disassembled just to show how this is working. We've got a jaw crusher again, but as you see here, this is with the door. You've got an open grinding chamber which can be cleaned easily. On the rear side, we've got the moving jaw, which is doing this movement again. Crushing the samples by pressure. Of course, the door is closed during process. We'll do now. And fixed with the lashes here. So, and then the sample comes out down here and can drop into the hopper. Is going into the disc mill, which is shown underneath. So we've got a rotating disc. The sample is coming in from the door here and then is ground by friction between the two discs. I will now close the door and slide back the whole machine so you can see how this is
done.
Adjusted. And then you've got the hopper placed on here.
That's good.
Fixed and connected to the unit. Okay, so we'll close the machine now and start the disc mill.
Attach it.
And then we start the jaw crusher. Now I've got a sample of simple glass, which I will drop in. This piece of glass, sharp edges, be careful.
Staubsauger an.
Yeah. Thank you. So and this will be dropped in here. This one is finished. Just stop it. It's not completely done, but as you can see, it's connected to a vacuum cleaner, to a cyclone, and here we can collect the sample in this glass.
Yes, and it was really quick also because there's no intermediate handling time, it just flow through, right?
So now I will show the sample here. We've got the initial. So this is a brick as before. Another one, of course, and this is a sample after grinding. You can see, without lots of dust, we still create very good fineness, where the disc mill down to below about 100 micrometers. Yeah.
Yeah. So in principle, in the RS, we can get finer particles than in the DM200, but I think here for this reason it's okay. And I just wonder what happens if we really like to grind large sample capacity.
Okay.
So we have this small glass, that's fine, but we are thinking in more larger sample capacities for recycling especially, I think.
Well, here for the demonstration, I just used a 500 milliliter glass, which is connected here to this stand. If you want to grind larger amounts, you can also use a big vessel like this. This is 30 liter, which can be connected with a cyclone here on top, so you can grind up to 30 liters in one run. Yeah? So this is really recycling or preparing a huge amount of sample just in a rush, which is not possible with the RS300. It's only batch-wise 1 liter all the time.
This is cool. Yeah, then I think this was a quick demonstration of what we can do with the hard and brittle materials from the construction area. And now it's time to show you more examples, but coming back to the presentation mode with the slides. So thank you, Gerhard, for this demonstrating time here, and yeah, see you in the slides.
Thank you very much.
Okay, samples before and after preparation, as promised from the lab. We have shown you 2 samples there, but we have much more samples over here in the slides. And it's more or less showing you before and after pictures. So I do not go into each detail, which machine in detail with which gap and which speed and which time and so on. You can see this later on in the download package in the presentation if you're interested. But it is really impressive, I think, to see the before and the after pictures. For example, of construction materials like concrete, in the BB50 RS200 pre-crushed and fine ground, then you get a really fine powder of 200 micron. This large stone or brick, 10 centimeter, 100 millimeter feet size, was ground in BB200 and the fine grinding in an MM400. This is also very nice and impressive because less than 2 minutes in total, you can come to a very fine powder. Concrete block, 8 kg. This is too large to be thrown in a jar crusher, for our jar crushers at least. But when we just divide it once manually, we can put it the halves into BB300, and here also we have nice pre-crushing. Or asphalt. Asphalt is really nice because it sticks. It has bitumen, and this can really make your horrors because you find it everywhere and you do not grind it, you just plat it or flatten it or stick it. And when you use liquid nitrogen and you embottle this sample for the pre-crushing in a jar crusher, then you can really pre-crush the sticky material. And when you then use for the fine grinding step the MM500 control, for example, then you can also brittle the sample during the grinding in the fine grinding step. You won't get any sticking effects. So this is really a nice thing. With a sticky material, always think about liquid nitrogen, and if it's available to be unbrittled, and then the pulverization can also be performed. Yeah, even in this case. Wood is tough, wood is fibrous, but when we go to SM and ZM, for example, then we can pre-crush the wood or pre-grind the wood and fine grind it to what's in this case 150 microns or below 1 millimeter coming out of the SM. Or we can grind furnitures, for example, 10 millimeter particles ready to be fine grind in a ZM. Or we can directly, if the wood is small enough, go into the MM400 and pulverize it to 100 microns. Glass is also common in construction materials, maybe not glass bottles, but glass parts of any windows or whatever. And just the examples that you can use HM200, the hammer mold. This is really nice for the glass sample. Yeah, coming to 2 millimeter samples. Glass waste in a PM400, really finely ground to 20 micron particles, or 40 micron in TM300. This takes a bit more time because there's more mass and the energy input in a drum mill is not the same as in the PM. But in the end, after 3 hours, you have around 2 kg of this sample. Yeah. And glass wool as well in a SM and then in a MM400, 30 microns and let's say less than 7-8 minutes in total. For mining, we have chromium ore and an RS300 finely ground gold ore and a BB500, for example, pre-crushed iron ore and an RS200 finely ground, another iron ore and a BB200 and then an RS200. So also very nice examples. And then we have also some examples for ceramics, very hard material, tungsten carbide. This is nice. Here, of course, you need also tungsten carbide jars when you try to crush this, because if you have steel tools, this will be not nice. BB50 and MM400 was really cool for this kind of sample. Ceramic parts in the BB250, so the jar crusher, which was shown in the combo unit with the door, you can really come to 3 millimeter particles over here. As well for the ceramic green bodies, 100 microns when you use first a BB and then a DM200. And spent catalysts as well. You can fine grind in just 4 minutes using the BB250 and the RS300. Okay, I think I could give you much more particles, much more pictures. This is a selection. I hope you will find your sample materials as well over there. But, I also like to tell you something about sieving, splitting, and pressing, because it somehow also belongs to this complete topic. And then let's start with sieving machines. We have 9 models in our portfolio, and we work with 4 different sieving methods. You can see here in let's say orange, the AS200 tap, which works with tapping. Then in violet, AS200 jet, which works with an airstream, and for larger sample materials as well, the AS400 control, which works with horizontal movement. And the remaining others, they are working with 3D vibration mode, so that the particles are not just moved in a circular way, but also thrown in the air and can reorientate them. And you will see in the slide that this makes a difference to some samples if they use one sieving method or the other one. But just show you the sieve shakers, small ones, and the ones for bigger volumes, which are used for recycling purposes as well, I think. And the special ones for the tapping and the horizontal movement and the deagglomeration of some ground particles, and for fine particles, this is the AS200 jet. But you can see this on our webpage. This is easy to find and to see what are the different features of the machines. But what is really important to give you an impression about how to sieve. And again, here's just a short overview. There are lots of other recordings for sieving, which give you all details, but we have to talk here about overloading a sieve. Because when you overload a sieve, you won't have any effective sieving anymore. I just tried to draw this here with this slide. You see that the large particles are just blocking the pores of the sieve, and the small ones, which could pass the pores, they do not come to the pores because they are just laying above the larger ones. And this is not effective because you will consider this as large particles as well, when you weigh the sample back. And this means we need to talk about how can I find the right sieve for my sample. And this needs to be taken into account for two aspects, and they are according to DIN 66165. And we have to talk about maximum particle feed size, which is allowed per distinctive sieve. For example, with the formula you see here in this slide, we, for example, have a 250 micron sieve. How large can the particles be which I put on this? You put just the sieve size, or the sieve aperture size, 250 microns in this formula as shown, and then you come, for example, in this case, to about 3.8 millimeter particles. 3.8 millimeter particles, yes. And this means particles which are larger should not be put on the sieve, because then it's getting not effective anymore. If you have 4 millimeter, 4.5 millimeter particles, use first a 500 micron sieve or 1 millimeter sieve to separate the large particles, because then it's getting effective. And also, how much sample do I put in? Can I completely fill the sieve and then start the sieving? No, this is also not correct. And here we have another formula where you can put the sieve diameter, the mesh size, a millimeter, and the material density into it. And then you get the maximum permitted remainder on the sieve. So what sample material is staying on the sieve after the sieving process? And when you double this amount, you have approximately the initial volume you are allowed to put on the sieve. This gives you also a kind of feeling how much sample can be loaded on a sieve. First, to assure that it is effective sieving, and second, not to overload it, because when you put too much sample on, you can simply also destroy it, because the woven mesh might be too can be damaged when you put too much weight on it. Okay, and then we have also to talk about equivalent diameter. Expect you have a sphere, your particles are round of, for example, 1 millimeter. Then you can watch it from different viewpoints. It's always 1 millimeter, and it's really size. So the equivalent size is a real size. But if you have a stick, which is diameter 1 millimeter, but length is about 5 millimeter, for example, then the particle is longer than 1 millimeter equivalent diameter. It can pass through 1 millimeter pore size. For example, through a mesh size with the 1 millimeter, because it fits through it lengthwise, but it is 5 millimeter length. Means that the equivalent diameter is not the real diameter, not the real size, let's say it like this. And the coin makes it more obvious again, because a coin of 1.3 millimeter size can also be or fits through this 1 millimeter mesh size sieve. And it seems that it is finer than 1 millimeter, but it isn't, because it's 1.3 in diameter. So be a little bit careful with the shape of the particles, and look about the equivalent diameter and the real size. And if you like to distinguish between this, you need an optical instrument to provide more information about the particle shape. And sticks might be detected as spheres or coins, and maybe falsifies your results. And this is also an example here from less theoretical point of view. It's wood and plastics, and you see that this wood particles, they are not round, they are flakes, maybe flakes, flat particles, elongated particles. If you use a horizontal sieving, then they stay on the sieve because they do not change their orientation. They just slide on the sieve because it's not a 3D motion. Yeah, it's just horizontal movement, circular one, and then they seem to be as real or in the size as they are really. But if you use a vibratory sieving, as shown with the elongated particle here of the plastic, you see that with throwing the pieces into the air, then they can reorientate and they can pass lengthwise. And this falsifies also your results, maybe. Yeah, you can see this same sample material sieved in different sieving machines with different sieving methods, make different particle size distributions. And for example, the wood chips here with the IS 400. Sorry, it's late in the afternoon. Here you can see that you can also fractionize it correctly with this sieving machine. On the left-hand side, you have the finest particles, and here on the right-hand side, you have the large fraction, 60 millimeters. Yeah, that's the right choice to separate and to fractionize those elongated particles. And on the other hand, plastic pieces, here you can use vibratory sieving, for example, because they are more round plastic pieces, and that's a good way to sieve this one. So 2 millimeter, less than 2 millimeter on the left-hand side. On the right-hand side, here is a large fraction, which is larger than 6.3 millimeter. Just an example for fractionizing such a sample. And I think that's 2 slides left. So one for sample splitting PT 300. So you see the size of the instrument with the lady who stands just beside it. And here you have a rotating drum, let's say it like this, and a constant volume flow of your sample. In this case, it was peas, and they were just put into the different container of this rotating drum. And here we have different choices, so we can use continuous outlet with one compartment which collects a part of the sample. The rest is just going through this continuous outlet. You can put in a segment with 4, or for example with 6 or 8 different ones, and also with different volumes. But what is important, because of the constant sample flow into it, you have the same composition of the sample in each compartment. The volume can differ, as in the last one here, but the composition is the same in each of them. So in terms of percentage, for example. And if you now have the task, for example, to pre-crush and fine grind some material, then it becomes crucial that you have good sample splitting maybe in between. So if you have 60 liter sample, for example, which can be used in a pre-crushing step in the BB50, yeah, you get this pre-crushing. Then you have maximum feed size for the PT300 is 30 millimeter. So you need to crush it to less than 30 millimeter in the jaw crusher. And then you can take, for example, the 60 liter configuration of the PT300. And now we have the different compartments which you can put in. If you take the one which splits it into 4 segments, then you still have 4 times 50 liter sample. This is a lot of material for fine grinding, except you go to a TM300. But you can also use the compartments which split it into 10 part samples, and then you have, of course, 10 times 6 liter sample. Then you can take one of these compartments and split it again, and then you have 600 milliliter part sample. And this can be easily be fine ground in RS300. So here you can, for example, from pre-crushing over sample splitting to fine grinding step. Okay, I forget, there's one more slide again, except the scientific one. Sample pressing, of course. So we can use our PP40, our tabletop machine to press smooth pellets for wood, cellulose, or slacks, for example. Here you see we get stable pellets with smooth surfaces for XRF analytics. And a really short time, we can do it stepwise, by increasing the pressing force from 10 to 20 to 30 tons, for example, or if it is just needed one pressing step in the case of slack. And sometimes we can do what we want. We won't get a stable pallet because it just comes out of the machine and is pulverized again. But in this case, we can use Licovax to stabilize the pellet. So we mix our sample in a specific ratio with Licovax. We can do it by hand manually, or we use our MM400 with a vacuum tube adapter, where we just do the mixing automated in an automated way and quite quickly. And then we take one of these flasks, put it into the PP40, and then we get also stable pellet over here. So maybe a nice tool to facilitate your daily work. Okay, then the last slide, the way we use or where the Retsch instruments are used in R&D projects. There's one R&D project which uses the high energy ball mill Emax, which gives really high energy input so that it is able to crush the hardest materials. This is used for mining waste, and then some of the mining waste ingredients is then used to be used in new thermoelectric devices. And of course, this helps to minimize the mining waste. This is a nice project, I think. Another one is using the PM400, where, for example, porcelain is recycled and repressed into new porcelain. And this study aims to find out if there are differences to the traditional way or not in terms of quality, for example. Another project here is also to reduce hazardous mining and industrial waste. So that by grinding those kind of waste, maybe there's the chance to reuse it in aluminium composites by mechanical alloying techniques, for example. And another one uses the TM300 from some waste also, which is very toxic because it may release chromium-6, which is of course very dangerous also for the groundwater. And yeah, by reusing this material, you minimize the risk that it affects our groundwater, and maybe you can also use some minerals coming out from this waste again. So this is a research in this case. So I think very interesting and really forward or straightforward, future-orientated approaches. Okay, then before I think there's time enough for answer to, let's say, maybe maximum 3 more general questions. The last slides here. Please just visit our recycling landing page as well. Just scan the QR code or register for the 3 upcoming webinars which deal with other sample materials like plastics or also maybe like more wood paper and food residues, for example. So just have a closer look to this. I will be glad if you are there as well. Okay, and then I look to my colleague if there have been some questions of more general interest. Yeah, there was some question for feed size of the hammer mill. What is the maximum feed size of the HM200? It is 100 millimeter, but be careful, don't throw a stone of 100 millimeter into the hammer mill because this is too much material, too hard material for it. But maybe softer material like dog food stick. This can be up to a size of 10 millimeter, no problem. The stone should be maybe 30 millimeter, 20 millimeter maximum size, then the machine can cope with it as well. Okay. And what is the maximum feed size of the SM300? The SM300 has a maximum feed size of about 60 to 80 millimeter. It depends a little bit on the orientation, how you throw in the sample material, but again, also have a closer look on what you throw in. Yeah, compact wood block, maybe take a smaller one. If it is a twig, no problem. Yeah, so it depends also a little bit on the sample properties, what you can do there. Okay, and one last question maybe for not only sticky material like the asphalt I have shown, but really wet. So dripping wet samples like slacks or some kind of filter cakes. Yes, this is an awful sample, I know. You won't throw it into a BB. It will only be a huge cleaning effort, not nice. You can put this in an RS200 or 300. It will be also not nice for cleaning, but at least it will just be in this closed vessel, yeah, or in a ball mill. You can try to put it into a ball mill, because then you have to just cleaning effort of the bowl and the balls. I think the RS200 and RS300 are the best options for this dripping wet samples, yeah, if you cannot dry them, because drying of course helps to pulverize it. Yeah, okay. I think then I have to close this webinar session. It was really a pleasure to talk to you and to hopefully help you in your daily work. Don't hesitate to contact us for any more questions, and then I'll say thank you very much and goodbye.